Bismillahirrahmanirrahim. So the topic for this lecture is review of complex numbers. So we must have already studied complex numbers, but we'll just give a review of short review of the complex numbers. So a complex number in rectangular form, you must have studied it like this: x plus y iota, right? So this is the real part, and this is the imaginary part. Uh, but first thing that you must know that in electrical engineering, we usually don't use this iota here in the complex number. We usually use the number j, right? J is equal to minus 1 square root, because I is usually used to denote current, right? So I is used to denote current, so that's why we use J in the imaginary number. So for example, this complex number will be written like this: x plus J y. So you note that we also write J here in front of the imaginary part, not here. Not We do not use it like this: x z is equal to x plus yj. Though it is correct, but it's the convention, particularly in electric circuits, that we write the number complex number this way. J is written in front of the y here. So for example, if we have a complex number za is equal to 2 plus j4, so it's not written 4j, right, but j4. So, uh, so j is equal to minus 1 square root, and you must also know that if we take a square of j, that should be equal to minus 1, right? And 1 over j is equal to, for example, 1 over j into j over j, so that will be equal to j over j square. J square is minus 1, so 1 over j is equal to minus j basically, right? So these are the small things you must have already studied, but uh, we are giving a review so that you must recall them. So this is the rectangular form of the complex number. A complex number can be written in three forms. One is the rectangular form, that is z is equal to x plus jy. The other is polar form. For example, z is equal to r angle phi, right? And the exponential form, z is equal to r e j phi, right? So these, the polar form and the exponential form, these are quite similar, right? Both are represented in terms of r and phi, and all these three forms can be related to each other. For example, if you know the Euler's identity, which is basically E j theta is equal to cos theta plus j sine theta. This is Euler's identity. So if you use this Euler's identity with this exponential form, so it can be written like this: r e j phi is equal to r cos phi plus j r sine phi. So if we compare this equation with this one, so you can see that this is the real part, this is the imaginary part. So comparing with this one, we can say that x is equal to r cos phi and y is equal to r sine phi. So using the Euler's identity, we can find the corresponding rectangular form from the exponential form, right? So this is the conversion basically from the exponential form to rectangular form. And we can do the vice versa also. For example, if you take the square here of the both sides, so this was conversion from exponential to polar. And now we are going from polar to exponential to rectangular, sorry. And now rectangular to exponential. If we take the square of both sides, so then x square is equal to r square cos square phi, and y square is equal to r square sine square phi. So add both these equations. So x square plus y square is equal to r square cos square plus cos square phi plus r square sine square phi. So that will be, we take the r square common, r square into cos square phi plus sine square phi is equal to x square plus y square, right? So that x square plus x cos square phi plus sine square phi is 1. So that is r square is equal to x square plus y square, and r is basically is equal to x square plus y square square root, right? So using this, we have found the r value of r here, given the values of x and y, right? In terms of r is expressed in terms of x and y. So likewise, uh, we can find the value of phi also given x and y. For example, divide both these equations. For example, uh, r sine phi divided by r cos phi is equal to y over x. So that leaves us with tan phi is equal to y over x, and phi is equal to tan inverse y over x. So again, we have found phi in terms of y and x. So uh, given the rectangular form, the rectangular components x and y, we can find the exponential components x and y. So if you see, I've already described these polar and exponential forms are quite similar. They are both expressed in terms of r and phi. So if we have exponential form, we have the polar form as well. So in other words, we can write uh, r e j phi is equal to r phi is equal to x plus jy, and that is equal to r cos phi plus j r sin phi. So given the rectangular form, we can find both the exponential form and the polar form. And here, given the rectangular form, given the polar or exponential form, we can find the rectangular form. If we have phi, either from the polar form or the exponential form, and if we have r, either from the polar form or the exponential form, we can find the rectangular components x and y. And conversely speaking, if we have x and y from the rectangular form, we can find the r here, right, and phi here from the rectangular components. So in a way, it's a conversion from exponential r polar to rectangular, and from rectangular to exponential r polar form, right? And this is polar also. We can write polar or exponential to rectangular form. So this can also be expressed graphically. For example, take this is the imaginary axis, this is the real axis, this is the real axis, this is the imaginary axis. We have origin here. For example, this is minus j min minus 2j This is j, this is 2j and 3j and 4 on, so on. And for example, we have a x component here on along the real axis. This is x here, and we have a y here along the, for example, imaginary axis. So this is the real part x, and this is the imaginary part y, and the resultant is here, right? This can be represented with r, and this is the angle phi here. So again, this forms out to be, if we consider this a right triangle with the vertical component this and the horizontal component along x-axis, then we can again find r using x square plus y square square root. This gives us r here, right? And we can find phi from tan inverse of y over x. And similarly, we can find the rectangular components from here. For example, if we have the this polar form or exponential form available with us, so you can see that y is equal to uh, uh, sorry, uh, y over r is equal to sine phi, right? And we can say that y is equal to r sine phi. Likewise, uh, x over r is equal to cos phi, and we can say that x is equal to r cos phi. So given the uh, polar form or exponential form, we can find the y component and the x component like this here from the graphical representation also. So this concludes our review of the complex numbers.